Okay, 3.9, we are looking at tangent lines and linear approximations. So you guys will notice that the section says 3.9, but there's actually a lot of these problems we're going to just give you a worksheet from. It matches up more with what's on the AP test. So some of this stuff you're probably familiar with. We're just kind of putting it all together now. So a tangent line. So this is what we're looking at. You can see this red curve right here. And a tangent line, remember it touches once. You can see the tangent line is right here. Remember the derivative at this point is equivalent to the slope of the tangent. Okay, so two important things to notice when we're looking at this. That this point over here, let's call this, if we want to call this A, then the ordered pair is A f of A. And the slope here, now remember what we just said, that the slope of the line is the derivative at that point. Okay, so the derivative f prime of a is equivalent to the slope. Now if we were to write it out, we would say, remember it's y minus, we have to fill this space in, x minus, fill this space in. So this is how we want to think of point slope. Remember, this is how we write lines this year. So over here, minus the x is going to be another x value. Well, look up over here, what is the x value? And it's actually an a. And then what is the output if we're dealing with the function of f of a? Now right here, this should be our slope, but what's our slope? The derivative, right? We're past calling it m, now it's the derivative at a. So we're going to use this tangent line a couple times today for different applications, okay? So this is, I know we've made it before, but now we're going to start applying it and see how it would look on some of these problems. Okay, so we have this problem right here, and it's asking us to find the equation of the line tangent to the graph. So what that means, at 0, 1 is where it's touching. So how about we start making our answer? We can say that we have y minus the output. If the input, I'm just going to write it in the form, if the input is 0, the output is f of 0. So y minus the output equals the slope at 0, and then x minus 0. Well, we know f of 0 is 1 because they told us that right here. The only thing I don't know is the slope, so I'll get back to that, and x minus 0 is x. Well, remember what we said up here, that the slope is the derivative at that point, so let's find this derivative. So we're going to say dy dx, the derivative of 1 is a constant, so that's 0. I'm sorry, the derivative of 1 is 0, because 1's a constant. The derivative of sine is cosine. Okay, now if we want to find the derivative at a value, okay, so the derivative at 0 now, because remember we want to find the slope at 0, that's what this says, okay? So what we can say is at x is 0, the derivative is going to be cosine of 0. Okay, and then cosine of 0 we know is 1, so we just found f prime of 0, and a 1 can go there. Now that looks kind of weird with the 1 times x, so how about we just add this one to the other side, just so it looks a little nicer. So y equals x plus 1. So what we just found was the equation of the line tangent to the graph at that point. And just matching things up, y equals mx plus b, you guys see the slope is 1, the slope is 1. Okay, so going on to this next problem. So I kind of walked you through something here, but I'm going to go ahead and draw a graph, and you do the same in this space over here. Let's go to 3, 4, let's go to 4, and up to 2. Okay, just so we have that as we're reading it. So it says that the tangent line to a graph can be used to approximate. Okay, so we've been making tangent lines. Now let's see why we're doing them. It's to approximate the values of the given function. Okay, for example, and then they give you this line here, is tangent to this graph. So I already found the tangent line for you. We're going to go ahead and confirm it, but how about we graph this? So to graph this point, we have 0, 0, we have 1, 1, and we have 4, 2. Smooth that out there. Okay, so what we just found here was f of x equals root x. Now, they told us the tangent line, but let's confirm it. So if we have a tangent line, what is it going to look like? So let's draw a space here. And they're claiming that this is to estimate or approximate. So they're giving us this graph, okay, and then they're doing the tangent line. And we haven't explored what they're doing with it yet. So let's just confirm that that is the tangent line at x equals 1. So let's write our standard form. if it's at when x is 1, this is the output at 1, this is the slope at 1, and that's 1. Well, we know the ordered pair, and it tells you right here even that it goes through 1, 1. So right away we know that the output is 1. Again, this is what we're going to have to find is the derivative. So let's go over here and find the derivative. F of x equals x to the half. Notice I'm writing it to the half because it's more calculus friendly. We bring the half down and decrease it by 1. So now the derivative is equal to 1 over 2 root x. But we don't want the overall derivative. Remember, we wanted the derivative at 1. So the derivative at 1 is 1 over 2 square root of 1, which is a half. So now we have the derivative at 1 is a half, and we can fill this in. This is the equation of the tangent line. Now look at how they wrote it, which is totally fine. They manipulated a little bit. So if we do that to ours, do you guys see if we distribute this half here, we get a half x? If we distribute the half here, we get a negative half, but then we have to add this one over. So now that's a plus half. Okay, good. So they are right. We're checking their work, and they got the derivative, and so did we. I'm sorry, they got the tangent line, and so did we. So let's go ahead and graph that now and see what they're doing with this. So this line, okay, this line that I drew is tangent at the point 1, 1. See how it only touches once. Okay, this is the equation, y equals 1 half x plus a half. So I'm going to go ahead and write that in. This is y equals 1 half x plus a half. This right here at 1, 1 is the point where it's tangent. Okay, so we know where 1, 1 is. Now, let's think, now why did we do all this? So this is what we're used to. So what it says is, going back up here, is the tangent to a graph can be used to approximate the values of a given function. So if we keep reading, it says near the point of tangency, which is this point right here, it says the tangent line is close to the curve. So look at right here. Look, see the tangent line is slightly above the curve, and over here the tangent line is also above. Over to the right, it's way above. So the point that they're making is close to the point of tangency. The tangent line is super close to the curve itself. So outputs from the line, so these y values should be close to the actual values on the curve. So they're saying, can we use this tangent line to approximate what the value should be at 1.2? Well, let's go ahead and do this. So over here, this was our tangent line. If we use a tangent line approximation, I'm going to abbreviate. Our tangent line again is right here. They're saying what is happening at 1.2. So let's go ahead and sub a 1.2 in for x. And you'll see that you get 1.1. Okay, so the ordered pair at 1.2 on the tangent line, remember this is not exact, is 1.2 comma 1.1. So we subbed 1.2 into the tangent line to find what the value is. Now we agree that this pink is super close to the blue, so the answers are going to be really close. Then let's go ahead and find out what the actual answer is. Well, the actual value is going to be f of 1.2. The function was the square root of x. If you look up here, right, that's what this curve is right here. So if we sub a 1.2 in, out you are going to get square root of 1.2, which is 1.095. So this point on the curve itself, which is right below it, is 1.2 comma 1.095. Now you can see that they're super close, right? So we're trying to illustrate to you that yes, the tangent line approximation, if you're right next to the point, is going to give you something really close. Okay, so you're going to be asked to do this quite a bit. But then I'm hoping that the question that you have is, why would we ever want to? Like if I could come over here and find the square root of 1.2, why wouldn't I just do this? Why would I go through all of this work to approximate the tangent line? Well, think about it for a sec. Why would you? And I would hope the only thing you're thinking is if you're forced to, right? If I had the square root of x function right here, and I'm able to sub in a 1.2, I don't want to do all this. But if I didn't have access to this, wouldn't I be stuck? And I wouldn't have anything to sub 1.2 into. So if f of x isn't provided, then we wouldn't be able to do that. Okay, one other thing before we go on, I want you to notice here that the tangent line approximation produces an overestimate. We're going to talk about this a little later in more detail. An overestimate, and let me say at x equals 1.2. Okay, so what I'm telling you here is, if you look back up here, 1.2 was the value of the tangent line. Because the tangent line is above the curve, do you guys see that? Then if I use the tangent line, it's always going to give me a number above what it should be. Okay, moving on. Example 2, for this function f prime is negative 2x plus 1. Okay, if they tell me that f of 1 is 4, I know that that's an ordered pair. What is the approximation? Here's what they want me to approximate, found by using the line tangent. And then there's our keyword that we're going to see a ton of today, using the tangent line, the line tangent, at x equals 1. Well, we can't take this x equals 1 and sub it into anything, or I'm sorry, this 1.2 is what they want, because they never gave us f. So I hope you're seeing here where we have to use the tangent line. We don't have an f to sub 1.2 into. Okay, so what we're going to do first is let's start making our tangent line. So if we remember, we went back here, we went ahead and we made our tangent line, then we subbed in the number that they want us to approximate. Okay, and we got our 1.1. We agree that is not exactly correct, but in this problem coming up, we don't have a function to get the exact answer. Okay, guys, so let's go ahead and do this. If it's at the point 1, 4, we're going to have y minus f of 1 equals f prime of 1. I just realized there's a lot of 1s here. And then x minus 1 on the last couple examples. Now, what do we need? Well, we need f of 1, right? Look at, we have to fill this in, and we already know that. But f of 1, they told us, is 4. So we can go ahead and sub that in right away. So y minus 4 equals f prime of 1, x minus 1. So now what's the only thing left is f prime of 1. Well, first we need to find f prime. So f prime of x is negative 2x plus 1. Oh, you know what? We didn't even have to find it. They gave it to us. Now, make sure if you're finding the derivative at 1 that you sub a 1 in here instead of an x. So now you have negative 2, 1 plus 1. So f prime of 1 is negative 1. Well, that was the only missing piece over here. So now our final equation is y minus 4 equals negative 1, x minus 1. The only thing left to do now is they told us to use the tangent line to find out this value right here. So our tangent line, which is over here, we can clean it up a little bit. We could have, it simplifies really nicely, negative x, if I distribute, that's a plus 1. And then if I add this 4 over, that becomes a 5. Now I want y at 1.2, because that's what they said. They said find the tangent line, which we did. Then they said use that to approximate. And that is going to be negative 1.2. Oops, let's fix that. You guys go ahead. Negative 1.2 plus 5. So f of 1.2 is approximately 3.8. Notice that this is not exactly, right? It's definitely approximate. The tangent line is not technically touching the curve anywhere else except at that point. Okay, so at 1.4, this tangent line touches the curve. At 1.2, it doesn't. So that's why that's an approximation. Okay, going on. Example 3. The function f is twice differentiable. Look at, they gave us an ordered pair. Now here, I'm trying to give you different ways of writing this. Here I gave you f2 of 1, and I gave you f prime of 2 is 4. Up here, we had to go through and find all that. Let's see if I can show you. We had to find f prime, the value. Now they gave it to us. Again, they're asking us to use the line tangent and approximate 1.9. So we're using the tangent line where it hits at 2 to approximate the value of 1.9. Notice that it's close. So let's write our tangent line. Right here, this is the ordered pair 2, 1. So I'm going to say y minus f of 2, because 2 is my input, is f prime of 2, x minus 2. We know the output is 1 because they told us. Oh, look at, this is awesome, because they also told us f prime of 2 is 4. We're not doing any work here. Because we're going to be subbing a number in, we can clean this up and get 4x. Remember right here, this is going to give us a negative 8, add the 1 over negative 7. This is our tangent line. This is the tangent line to the function f when x is 2. Okay, now we're going to go on and we're going to approximate 1.9. So now we're going to say, let's sub a 1.9 into our tangent line. and we'll get 0.6. So f of 1.9 is approximately 0.6. Okay, just one more. Look at this curve right here. What rule are we using, guys? Try to think about it. This is an old AP question. We're going to use implicit because we have y's embedded in the problem that we cannot isolate. Write an equation for the line tangent. Okay, we're used to this. Let's go ahead and start off with, well, what do we need for the line tangent? It's going to be y minus the output at 4 equal to the derivative at 4 times x minus 4. Okay, well, we know that we're going to dump numbers in. What numbers are we going to dump in? The output, the slope, and we know that. Well, we already know the output, so we can go ahead and write that in. Y minus a negative 1 gives us y plus 1. And I don't know why I put that parenthesis there. Now, we don't know the derivative. This is what's going to be a little tricky for us now, but we do know the input is 4. So once we fill this in, this will be our answer. Because all they said was write an equation. Okay, let's knock this derivative out. The derivative of negative 8x squared is negative 16x. Now moving on to the second term, 5 is your scalar, so write it out in front. Because you're multiplying two things, we're going to use product rule. Okay, so these two things being multiplied right here. So it's, remember, first derivative of the second, second derivative of the first. So first, what's the derivative of y? dy dx, plus the second, which is y. And what's the derivative of x? dx dx, which we call 1. Plus, imagine this y is in parentheses. You bring the 3 down, y squared, and what's the derivative of the stuff inside the parentheses? dy dx. We have a negative 149. That's beautiful because that derivative is 0. Okay, next step. Now remember, if they ask you for implicit, this gets kind of crazy because look at dy dx is embedded in the problem. We have to isolate it and go through all that work. But they never said find dy dx. Our only point is we want the derivative at 4. So let's look over here. They gave us a point, and let's replace all the x's and y's. I like doing it right away to make the algebra a little easier. So negative 16x is 4 plus 5, x is 4, dy dx, y is 1, plus 3, y is negative 1. So negative 1 squared dy dx equals 0. Okay, now just go ahead and do the math. So we're going to get negative 64 plus 20 dy dx. Don't forget we have this 5 we have to distribute, minus 5 plus 3 dy dx equals 0. Our goal is to solve for dy dx, so let's combine all like terms. You have a negative 64 and a negative 5. That is going to give you a negative 69 on this side. Then you also have a 20 and a 3, so that's 23 dy dx, but let's throw that to the other side. Let's go ahead and solve for dy dx. So dy dx is, what is that, 3? And you know what else I wanted to tell you is this is the derivative at 4 negative 1, right? Because this top line gave you the derivative in general. Then at this point I plugged in 4 negative 1, subbed in. So dy dx is 3. So now I can go ahead and replace my derivative up here with 3. That was the derivative at 4, 1. So final answer is y plus 1 equals 3x minus 4. They didn't ask us to do anything with it, just make a tangent line, so we're done. Okay, going on. Now it says there's a number k so that the point 4.2k is on the curve. Okay, so 4.2k is actually on the curve. We don't know what value when we sub 4.2 in that we get out. So then it says use the tangent line found in part A, approximate the value of k. Well, aren't they just saying that I want to sub 4.2 into the function, right, to get a y out? They're saying, you know what, don't worry about that. How about you just sub 4.2 into the tangent line and see what you would get? So let's look at our tangent line again. We have y plus 1 equals 3x minus 4. We're going to go ahead and replace x with 4.2. Okay, and now we just have to do the math. So we have y plus 1, 12.6. Don't forget to distribute minus 12. So y is going to equal, on the right, you have a 0.6. If you subtract 1 over, you are going to have a negative 0.4. So that's our output for k. It's approximately negative 0.4. Okay, that's a wrap. See you later.